Okay, welcome. This video is about practicing for our mid-unit assessment for forces. We're just going to solve some problems here from the guided notes. This is from page 13, 14, 15. I've taken these like number one here. I'm just going to move them to the side so I have some more space to work it. I have some timestamps in the description, hopefully get us quickly through it. Now, just a note about the test. Main things that we care about for this week when we're taking our test. Number one, make sure we can draw free body diagrams. Okay, that means we have a dot to represent our object. We have arrows of appropriate length for our forces. A longer arrow means a larger force, a stronger force, and its direction also matters. So make sure it's pointing in the correct direction, like normal force perpendicular to the surface. And then we got to make sure we label those with the correct labels, like Fg for the force of gravity, Fn for normal force. Our second thing is then going to be solving for something like, let's say the acceleration, or maybe an applied force, or maybe finding the frictional force or something like that, or maybe solving for mass. And that means the equations that we're using that we'll see on our equation sheet for the test will be the second law equation, sigma F equals ma, or the other way we write that, F net equals ma. Remember, sigma F or net F means the total force, so you look at all the forces acting on it. And the other equations we might use would be Fk equals mu k times the normal force. That's from our friction. Remember that our mu k is the kind of stickiness factor that ranges between 0 and 1. That determines like how sticky the materials are together. That bigger number, more friction. And then our normal force, Fn, is going to be the strength with which they are pushed together. So if that's bigger, that also affects the friction. So we know there are a lot of ways we can find normal force. It depends on what other forces are acting on our object, but we need to make sure we can find that. Okay. The other equation that might be on there would be if we had static friction at its maximum, then that would be equal to mu s times the normal force. But really the only ones you guys need to be worrying about are make sure you can use that second law equation and this kinetic friction. We're not going to have any static friction on the test. Okay, let's get going. This number one. Hockey puck slides across a flat piece of ice. The ice is not perfectly smooth. It's not perfectly smooth, so we have friction. The coefficient of kinetic friction between the ice and puck is 0.05. I'm just going to list some stuff down below to keep track of it. 0.05 is a coefficient of kinetic friction. I was also told my mass at the top, let me get that down, 0.4 kilograms. What's the magnitude of the kinetic friction acting on the puck? So that's saying, what is Fk? That's some amount of newtons of force. What is the acceleration of the puck? That's what is A. We want to get that in meters per second squared. And then the last part, if the puck has an initial velocity of 10 meters per second, how far will it slide before coming to rest? Well, that means final velocities. 0, how far it slide will be a delta x. Okay, this stuff down here, VI, VF, and delta x, that's a kinematics part of the problem, like a follow-up problem to the problem. Okay, the stuff about forces is going to be on our test. That has to do with this beginning first part of the problem. So we're just going to look at the first part of the problem together. The answer for our how far, when you go and check with your kinematic equations, you should get 100 meters. Okay, really far distance that it's going to fly. But we're just going to focus on that stuff bracketed up there in blue for our forces considerations. Okay, we're just looking at that stuff. Let's get this out of the way for a second. We're going to come over here. We know the first thing that we're going to need is a free body diagram. So let's get that going. We got a dot. I'm not told in my problem which direction this thing is moving, so we're going to say it's moving to the right. Just going to show that over there. The velocity is moving to the right. That's not part of my free body diagram. That's just to remind me, hey, this is the velocity of this object right now. It's moving to the right. It's going to be slowing down because we know it comes to rest eventually. So that means its acceleration must be to the left, in the opposite direction if we're going to have slowing down. Okay, what forces do we have acting on this thing? We've got Fg always. Right there, Fg always equals mg. It's important to know. We've got normal force. We have no indication of any acceleration in the vertical direction. So this normal force right here must be balancing with our Fg. And then we've got a kinetic friction. Since it's moving to the right and slowing down, we've got a kinetic friction F sub k. Remember, lowercase f for friction, like that, and we're good to go. When we look at the sum of the forces in the x direction, we're just looking at all the forces parallel to the x-axis, so that's just going to be Fk. Now it's good to decide what direction is going to be positive direction, which direction is going to be negative. It's good to state that right at the beginning. I'm going to call to the right positive because it's moving to the right. You'll get the same numerical answer if you call to the right negative. It's just the plus or minus sign. That'll be different. Remember, plus and minus sign is telling us the direction. Okay, so for the x direction, I've got minus Fk if to the left is negative. Those are all the forces acting in the horizontal or x direction. It's just kinetic friction equals mass times acceleration in the x. We want to find acceleration. So I get minus Fk over m equals a sub x, acceleration in the x. Now I know the mass, that was the 0.4 kilograms. I don't know the value of the kinetic frictional force, but we do always know, like boxed up here, right there, our kinetic friction is equal mu k times the normal force. It's going to be very important. We need to know that for the test. That's why it's on the equation sheet. I can substitute that in for Fk. I got mu k times normal force. Okay, over my mass is acceleration in the x. Okay, we know mu k is 0.05. That value has no units. It's the coefficient of kinetic friction. It's like the force divided by another force, like we did in our lab. It has no units. Normal force, if I look back at my free body diagram, my free body diagram shows, okay, normal force in the vertical direction, that needs to be balancing with Fg. So normal force has to be equal to mg. So it's going to be m times a little g. I've got a mass down here. We can solve all of this with just our variables, but I'm going to keep everything there and put in my numbers. My mass was 0.4 kilograms. In our problems and tests, little g can be 10 meters per second squared. We've got a mass, again, over 0.4 kilograms. We can see that 0.4 canceling out, and we're going to get 0.5 in the negative direction for our acceleration, and that's going to be in meters per second squared. So here's our acceleration in the x. I got minus 0.5 meters per second squared. That's my acceleration in the x. If you called to the right the negative direction, then you'd get a positive 0.5 meters per second squared. Either way, that acceleration has to be to the left in the opposite direction of the object's motion. The only thing to indicate in the y direction here would be these things that we have highlighted in the y direction. I see I've got a normal force in the positive direction, minus Fg is mass times our acceleration in the y is 0. So that means we got normal force equals Fg, and this matches our free body diagram. It matches what we substituted in for the normal force being equal to mg right here. And so if we wanted to show that, we would have 0.4 kilograms times 10 meters per second squared. Okay, that's the value of our normal force if we need to show that for newtons. Remember, we want every mass in kilograms, every acceleration in meters per second squared, and that guarantees our force is going to be in newtons. Keep everything in those units. Okay, let's look at the next one down here. We've got a box pulled at a constant speed. Oop, very important. Constant speed indicates that acceleration is 0. Now this thing is moving in the horizontal direction. It has an acceleration of 0 in both horizontal and vertical directions. So our picture here is just showing us it's being dragged to the right at a constant speed. Across a rough surface, that means we've got Fk, the frictional force. Mind you, also because the acceleration is 0, therefore, that means the net force is 0. All the forces must be balanced out. That's very important to see just from seeing the description of constant speed. We've got an applied force of 40 newtons. We've got an angle. What is the coefficient of kinetic friction? That means mu k is our question mark. And then what is the magnitude of the normal force, Fn? Okay. Now remember, we've got this equation for kinetic friction. Fk equals mu k times the normal force. And we're being asked to find mu k and Fn. And both those values are related to the kinetic friction. And if we know that the acceleration is 0 and all the forces balance out, then something's going to be balancing with Fk. And we're likely going to have to substitute in this expression for Fk so that we can find the values for each of those things. Like always, we're going to start with a free body diagram. Okay, we got a dot. We got to be careful. We got a force at an angle, so I want to make sure that I draw a reference line here because we've got the angle pictured up there at the top being some angle above the horizontal. I think it was 30 degrees. I forget what was, yeah, it is 30 degrees. Okay, so I'm going to draw that force first, just to make sure I got it in there. There it is. I'm making it nice and long so it's easy to see. There's FA. I could put in the value of that force too if I like. It was 40 newtons. And we've got our object moving to the right. You could put in as a separate arrow the velocities up there. I'm going to call to the right positive and to the left negative. Okay, we've got FG going straight down. FG always equals mg. I like to always write that so we don't forget. And we've got our friction to the left because we know it's moving along, moving to the right at a constant speed. So there's Fk. Make sure it's not just lowercase f, but Fk. We need to make sure we have that subscript. If it's kinetic or static friction, you have to show it. Now, what are we missing here? We're missing our normal force. Remember, when we have a force at an angle, that means we have part of our force. Liam, I'm recording a video. Can you wait, please? When we get a force at an angle, like we have here, a portion of this force in particular is pointing up. Okay, so it's kind of like it's helping the surface out. The normal force isn't going to be as strong. So I'm going to make sure I have a noticeably shorter arrow for the normal force right there. That means the normal force is not going to balance with Fg. Now, we got all our angles and all our forces in here, but now we need to make sure that we're showing how our force at an angle is resolved into its component pieces, or its horizontal and vertical piece. So here's my horizontal piece. Notice it's a dashed line because it's not a real force in there. I'm breaking it up theoretically into its little pieces. Here's Fa in the x direction. And then I have my vertical component or piece over here. Just like we did with projectiles, remember we want everything in horizontal and vertical pieces. So now I can see, since my acceleration and net force must be equal to 0, everything in the horizontal direction needs to balance out. So I can see right now Fk is going to have to equal the Fa in the x direction. That has to be the case if the net force is going to be 0, which it must because it's traveling at a constant speed. In the vertical direction, I see I have two forces pointing up, normal and Fa in the y direction. Now, both those forces pointing up are going to add up to a larger force, a total net force pointing in the upwards direction, and that's going to have to balance with Fg because the acceleration in the y direction is 0. Let's move this over to the side a little bit, make sure we're keeping everything in the right little spot there. Buddy, I need less noise, please. Sorry. Okay, here we go. In the x direction, we're just looking at what I've highlighted in yellow, x direction stuff. I'm going to call to the right positive. I said that already. So that means I'm going to have Fa in the x direction. That's positive minus Fk equals mass times acceleration in the x direction. Now, we also know our acceleration in the x direction is 0. And I'm also going to put in my expression for Fax, because we know that should be something we can find with the cosine function, because that red portion is adjacent to our angle. So Fa in the x direction, highlighted in yellow, that's Fa cosine theta, minus Fk. I could leave that as Fk for now, but we're going to have to substitute something in there. We showed that right at the beginning of this problem. Mu k times normal force is going to go in for that guy. So we got mass times an acceleration of 0. That means, like we see in our picture, and as we mentioned on our free body diagram picture, Fa cosine theta has got to be equal to Fk. Okay, so now we're going to substitute in, remember we said it right up here, mu k times normal force for the kinetic friction. All right, anytime you might have some true second law mathematical statements written and you don't know where to go, after that point, to see if there's something you could substitute in. We're only going to have two equations on our equation sheet. So here's our equation or expression for Fk, mu k times the normal force. Now we are asked to find both these values. We're asked to figure out what is mu k and what is Fn. So right now I have one equation right here where I know everything on the left side of the equation, but I don't know mu k and I don't know Fn. So I'm not quite ready to solve that part yet. I need to figure out what normal force is, and then I can go and figure that out. So let's go over to the y direction. We can find out what the normal force is. So in the y direction, I look back at my free body diagram. I'm going to call up positive. So that means I got normal force plus Fay minus Fg, that's in the negative direction, equals mass times acceleration in the y. Acceleration in the y direction is also 0. No indication we're accelerating in the vertical direction. So that's still 0. That means these guys that are in the positive direction will balance out everything in the negative direction. Fay is Fa sine theta. It's opposite our angle. And Fg is going to the other side of our equation. So there's Fg. So now I'm showing like what's in our free body diagram. Everything on the left side is pointing in the upwards direction. These two guys over here is got to be equal. When you add those up, that's got to be equal to FG, which is in the downward direction, because we know the acceleration is 0. All those forces got to balance out if the acceleration is 0. Now, for solving our equation, or solving our problem, we want to find out what Fn is. So I'm going to have Fg minus Fa sine theta, because I'm trying to isolate normal force. Okay, so Fg equals what? Mg, you always know that, minus Fa sine theta. Now we have a value we can find here. Now we could substitute in this expression right here. We could take this, and we could go put it in for normal force. Or we could get a value for the normal force right now, which I'm going to do. Mg, we just got to look back at our problem. What's given? We have a 25 kilogram box. Little g is going to be 10. Normal force is 40 newtons. And our angle is 30 degrees. I'm going to round, so I got 3 whole digits here. Normal force is going to end up being 230 newtons. Make sure you check you got degree mode in your calculator. And then we can take that value back over here to figuring out a value for UK. So I got Fa cosine theta divided by normal force, because now we know the normal force. The last thing we don't know is mu k. And since we know the normal is 230 newtons, we can substitute in applied force of 40 newtons times cosine 30 degrees over 230 newtons from our normal force is equal to mu k. And this should be a value between 0 and 1. So I should have 40 cosine 30 over 230. I should get about 0.15. No units for coefficient of kinetic friction. If you're solving for mu k on the test, please recognize there are no units here. And let's remind ourselves why. This is our equation that tells us kinetic friction. And if I solve for mu k like we were looking for in our lab when we were finding coefficient of friction, this is a force divided by a force. So I've got units of newtons divided by units of newtons. Those are going to cancel out. Mu k is just a coefficient, unitless, describing the stickiness factor between two surfaces. Okay, so we've got that guy solved, both mu k and the normal force. Oh, goodness. All right, we're looking at number 3 here, the coefficient of static. This is going to be a question that's relatively straightforward. One thing to remember for this one is that picture of what the graph looks like if you drag something and you get, if you got force in newtons over time, you're pulling, static friction's going up. It reaches a maximum, then it drops down, and then it's relatively flat. And static friction at a maximum is at this peak, which equals mu(s) times the normal force. So that's how hard you have to pull it to break it loose. And then we've got kind of this range here, which is kinetic friction, which is lower, less force to keep it moving once it's moving. Okay, so these are the two equations that have to do with this problem. If you're going to find the force it takes to get something moving, then you need to find out what force is equivalent to the maximum static friction. And then what force you need to keep it moving once it's in motion would be equivalent to the kinetic friction. So we'll take a look at this. We've got some information. The coefficient of static friction is 0.9. Let's list this stuff over here. Put it in orange. So we got a mu(s). So this applies when the object is stationary. 0.90. The box has a mass of 200 kilograms. It's a big boy. How much force must be applied to get it to accelerate? So there's going to be some applied force necessary to break it loose, get it moving. All right, so that's going to be the force that's got to overcome Fs at a maximum. And then we have the second part of the question is after here. If the coefficient of kinetic friction is 0.5, we say, okay, if it's moving, the coefficient is 0.50. How much force is necessary to keep it moving? It still has the same mass, but then we're saying, okay, what's the applied force necessary in that case? So we're just going to put these guys over to the side. So over there, we're going to say this object's moving to the right. We'll always start with our free body diagram. So we've got Fg equals mg. We're going to have some applied force pointing this way. This is going to be to the first part of the question, to break it loose, to get it moving. Okay, I got a normal force up here, and then I'm going to have some maximum amount of static friction. At a certain point, I'm pushing, 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 and then I get to the maximum amount of static friction. When I get to that point, I'm able to get it moving. In this setup, normal and gravitational force will be balancing one another out. They're only forces in the vertical direction. And then my applied force is going to have to be equal to or greater than this maximum amount of static friction. So if I go and look at the x direction over here, I see that my applied force could be in the positive direction, all that positive and that negative, minus Fs maximum is going to be equal to mass times acceleration in the x direction. And the moment, this thing has no acceleration because it's not moving at all. And then the moment I get to this Fs max, right at the peak, that's when it starts to move. So up until that point, I need to get my applied force to be equal to Fs at a maximum. If you ever see a problem that says what force is required to get it moving, then you're just trying to figure out what is Fs maximum. That's how much force you need to push or pull with. And Fs max needs to be equal to mus times the normal force. I can look at my vertical direction and see, aha, in this case, my normal force is going to be equal to the gravitational force. So I've got mus times mg, because the gravitational force always equals mg. So my applied force needed to break it loose, to get it moving, is going to be mus 0.90 times the mass of our object, which is 200 kilograms, times little g, which is 10 meters per second squared. I'm going to get a value here of 0.9 times 2,000, or 1,800 newtons, is what is required to break it loose or get it moving. And there's the first part of our question. The second part of our question is then, how much force does it take to keep it moving? And you might see that the only thing that's going to change here is our coefficient of friction is going to drop from mus, a 0.9, down to a mu k, coefficient of kinetic or moving friction, to 0.5. And so we're doing the same thing. We're just then saying, okay, in order to keep it moving, we still got our normal force. We still have gravity. Those are balancing out still. But now, because it's in motion, my kinetic friction is going to be smaller, because kinetic friction is a smaller frictional force than static friction. And so my applied force now is still going to balance with Fk, because I want to keep it moving at constant speed. But that applied force is just going to be a smaller amount compared to 1,800. So I go in here, I'm still doing the same thing. I'm saying, okay, to keep it moving, my applied force has got to be equal to Fk. Those forces got to balance. Fk is equal to mu k times the normal force. So that applied force is going to be not 0.9, but 0.5. Let's double check, make sure that's the right value. Yep, 0.5 is our mu k. Normal force is still mg, so I got 200 kilograms times 10 meters per second squared, because normal force equals Fg. And so I got half of 2,000, or 1,000 newtons. And that's the force required to keep it moving. To keep it moving at a constant speed, compared to the force in red, the force required to break it loose, to get it going. Okay, number 4 starts to get a little more complicated. We get a similar picture here that we've had before, a sled with a force applied at a downward angle. And we're trying to push it across a rough surface. So we got a coefficient of kinetic friction, we got kinetic friction acting on it. This question's asking, what must be the applied force to keep the sled moving at a constant speed? And then the second part is to figure out what must be the applied force in order for it to accelerate or speed up at 5 meters per second squared. So we're just going to start with number 1 here. Let's get a free body diagram going. We've got Fg. We'll always get that force right. Straight down, Fg equals mg. We got a force at an angle. Let's get that dashed line in there for reference. We've drawn a picture for this type of setup before. Make sure that our arrows for the free body diagrams always start on the dot. What is the angle here? 20 degrees? I want 20. Come on, 20. All right, so our force is going to be at a down angle. We got to start on our dot. So I'm going to make it long so it's a little easier to see. Okay, so there's FA. What is that force? Oh, we don't know. That's the question. All right, we do know our angle right here is 20. Let's put in a theta. Is 20 degrees. And then we've got a frictional force, don't we? But we're moving at a constant speed in part one of this question. So there's Fk. I know that's going to have to balance with the Fa in the x direction as I'm thinking about the length of my arrows. And then part of my applied force is pushing down, so that means my normal force is going to be bigger than Fg. Let's draw that a little longer. So there's my normal force. And then we'll just double check, looking through our problem, make sure we got all our forces. We got Fg, we got the applied force at a down angle, arrow of the applied force starting on our dot, going down to the right, just like in our picture at the top. Fk, we're saying we're moving this thing to the right, so Fk is going to be pointing to the left, parallel to the surface. Normal force is bigger than Fg, perpendicular to the surface. All right, we're looking good. Now we got a force at an angle, so we want to show its component parts. Remember, that's called resolving our vector. So there's Fa x direction, and here's Fa y direction in the negative direction this time. So now we've got a good free body diagram to help us get going. All right, now this one, you can pause and try to solve this yourself, but we are going to keep everything in terms of our variables here, and we'll see why. How it's going to be so useful for us. So in the x direction, I'm going to think about writing a true second law statement with F equals ma about the x direction. I see this force in the x direction. I see this force in the x direction. And I know for part one of my problem, remember it says to keep the sled moving at a constant speed. So I know that my acceleration in the x must be 0. So that means all my forces in the x direction should balance out. That means Fax should be equal to Fk. Now I can get more specific with how I write these. I could say Fa cosine theta, it's adjacent to the angle, equals Fk, which I could write as mu k times the normal force. Let's see, do we know the value of mu k? We do, it's 0.3. All right, so mu k here is 0.3, and we don't know what the normal force is yet, but maybe we can figure it out. So Fk, if I see Fk, I'm probably going to want to substitute in mu k times the normal force. Now notice our normal force is not equal to Fg, because if we look at the vertical direction, I see I've got a normal force is one force pointing up, and that needs to balance with Fg plus Fay pointing down. So you've got to be careful. All right, so I'm just going to pause right there for the x direction. I'm showing that Fa in the x direction is balancing with the kinetic friction. And then I'm going to go look at the y direction stuff. We just highlighted it. Right over here, we're looking at the y direction. Also in the y direction, the acceleration is 0, so I know everything's got to balance out. So I can write that as, okay, all the forces in the positive direction pointing up, normal force, must be equal to, they got to balance with everything pointing down. So that's going to be Fa in the y direction plus Fg. And then I can write that more specifically, Fa in the y direction, that's opposite my angle, so it's Fa sine theta, plus Fg is equal to mg. And now I've got two nice statements here. Here's number 1 in the x direction, and here's number 2 in the y direction. If we just go through these and we think about, okay, what things do we know the values of? Fa, we don't know. That's what we're being asked to find out. How hard do you have to push it with that green force Fa so that it moves at a constant speed? So that its acceleration is 0. It just goes to the right at a constant speed. We don't know Fa. We know theta. We know mu k. But we don't know the normal force. That's for the equation number 1. So we got two unknowns right there. We can't get a value for Fa from that, nor can we get a value from Fn. What if we look at equation number 2 over there? We don't know Fn. We just said that. We don't know Fa. We do know theta. We do know the mass, right? Where is it up there? 50 kilogram sled. That's our mass, 50 kilograms. All right, we got that. And we do know little g. So here we got two equations in purple, 1 and 2. And in each of those equations, we have the same unknowns. We don't know Fa, we don't know Fn. All right, so this is a system of two equations we want to solve. There are lots of ways we could do that, right? We could, like that, remember that lovely projectile lab challenge where we needed to solve a system. I'm just going to go with what might be the most straightforward right now, because I've got Fn isolated already right here. See, Fn is equal to this statement. The sum of the two forces pointing down must be equal to the normal force. So I could take that and substitute that in for Fn, and that's one method by which I can solve this system. So I'm rewriting equation 1 now, but I'm going to substitute in what I have underlined in orange. That's all I'm going to do. So I got Fa cosine theta. I just want to rewrite it and do the simple substitution by itself carefully to make sure I don't make any mistakes. So check it out. I got mu k times, and I'm going to open up some parentheses because I've got a plus sign in there. I got to be careful. Mu k times Fa sine theta plus mg. Okay, so I've just substituted in the expression for normal force. There it is right there. All right, at this point, when we go and look at what's unknown, we don't know Fa, we do know theta, we do know mu k, we don't know Fa, but that's the same variable, right? These are the same. I can get those together, hopefully, with some algebra. We know theta, we know m, we know g. So now we got one equation and one unknown. We just need to get that by itself. So I might do that by distributing my mu k here, multiplying it through to both terms, because I want to get Fa somehow, the Fa on the right side over to the Fa on the left side, or vice versa. I need to get Fa by itself. So for this one, I'm going to distribute mu k Fa sine theta plus mu k is multiplied over here as well, mu k mg. All right, notice this was just distributed. So this went to each term. And then I want to get Fa by itself, so I'm going to subtract my first term on the right side of the equation. Let's subtract that whole thing, mu k Fa sine theta. Those terms are being multiplied, so I got to subtract the whole thing right there. Equals what's left over on the right, mu k mg. And then I'm going to see, all right, I got Fa here. I'm going to factor so I can get it by itself. So I got Fa times cosine theta minus, now this other Fa's come out, so I'm just left with mu k sine theta. Gotta be real careful with my plus and minus signs there. Equals mu k mg. Make sure it looks like our k is a subscript here. Let's do this again. Mu k times mg. There we go. Okay, so now we can just get Fa by itself entirely. By keeping everything in terms of just variables, it's better for solving these systems, because if you rush to substitute in numbers and then you realize, oh wait, I don't have enough values. How am I going to solve the system now that I have half of these numerical values in there? The rest of the stuff's unknown. But if we just take our time and we're careful, we can isolate everything. And if you see like what's highlighted up here in blue, those guys are separated, we'll just kind of distribute everything out and then move them around, just like we've done here. We got Fa by itself. And here is, we'll use our little sparkly kind of thing. Well, it's not as sparkly as I thought, but there we go. That's our final expression there for the force required to keep it moving at a constant speed. Remember, this was part 1 of the question, where the acceleration is 0. This net force is what? And it's going to be found from this. And you make sure you can put that in your calculator properly. Now we got parentheses on the bottom there. Be careful that the order of operations is being carried out correctly. This should be 180 newtons. All right, the second part of this question then is okay, instead of having it move at a constant speed, let's have the same setup, but we want it to accelerate at 5 meters per second squared. Assuming to the right, because that's kind of the direction of our force, is downward and to the right. So if we were to take, let's go over here, we got some more space. Here's part 2, where the acceleration in the x needs to be 5 meters per second squared. My free body diagram, what happened to my dot, is going to be a little different now, isn't it? I still have Fg, that's not changing. We're still on the Earth, still got the same mass. We still have our, let's quickly get this reference line, and we still got the same applied force over here at a down angle of 20 degrees, right? And what's going to be different now is that this horizontal component of our applied force, it's going to have to be bigger than the frictional force if we're going to get it to accelerate. Right, before in part 1 we had Fk balancing with the applied force in the x direction, but now we want to get it to speed up, which means we need an unbalanced force to the right. So when I go to draw in my frictional force, I'm going to make it noticeably shorter than it was before, or noticeably shorter than the horizontal part of Fa. We're still asking what is that. Normal force is still going to be big because we have a bit of a downward force as well. Angle's a little messed up there, that's okay. There's normal force. So normal force is bigger than Fg because we still have this downward portion. We got our horizontal component of Fa happening, which is going to be bigger than Fk because we want to get this thing to accelerate. And this is the downward portion, Fay. Now we'll notice that this is going to look very similar, very similar looking answer, because now we just have the addition of something else. We want to make it a little bigger of an applied force so that we get an acceleration. In the x direction, our acceleration is not 0. Remember, it needs to be 5 meters per second squared. And I believe we do know our mass, right? Yes, 50 kilogram sled over here. Okay, so in the x direction, I've got Fax, I've got Fk, but I'm going to have an acceleration to the right. I call that the positive direction. And so that means that Fa in the x direction minus Fk, kinetic friction, is going to be equal to Max. And I know the mass, I know the acceleration, it's going to be 5 meters per second squared to the right, so positive 5 meters per second squared. And we're trying to figure out what Fa is, once again. Let's remind ourselves we also know mu k. That's still part of the problem, so mu k is 0.3. We used that in the previous part as well. All right, how can I be more specific? Fax is Fa cosine theta minus Fk is going to be mu k times the normal force equals Max. And then we can go through and we can say, like we did before, all right, I want to find Fa. That's my question mark. Do I know theta? Yep. Do I know mu k? Yep. Do I know the normal force? Nope. And be careful, if we just changed our applied force, we're pushing harder, then that's going to change our normal force. Because if we push forward and downward harder, then that's going to make the surface push upwards a little bit harder. So if you found a value for normal force from the previous part of the question, you can't just reuse it. Things have changed. Do we know the mass? Yes. Do we know the acceleration? Yes. So once again, we've got an equation like we had before that I called number 1 in purple with 2 unknowns. We go to the y direction. We'll get another statement. Now in the y direction, the acceleration is 0. So things not helicopter, it's not taken off on an airplane. We've just got acceleration to the right at 5 meters per second squared. So we go back and we look at our free body diagram. Normal force is up, Fg's down, Fay is down, just like we had before. Normal force minus Fay minus Fg equals 0. So that means our normal force must be equal to Fay plus the gravitational force. All the forces pointing up equal all the forces pointing back down. And so we can get more specific like we showed the previous step, same as the previous part of the question. This is Fa sine theta plus mg must be equal to the normal force. And we went through and we said, okay, we don't know normal force, we don't know applied force, we do know theta, we do know m, we do know g. So we've got a second equation now with the same unknowns, and we can solve that system. And we have, again, we could just say, all right, look, this Fn is isolated. Let's substitute this expression for the normal force, like we did before, in for Fn over here. And we can do that. And we're going to do that carefully, though. So we're rewriting equation 1 over here, red, minus mu k. And I'll open up my parentheses because I got this plus sign in there. Here's Fa sine theta plus mg, close parentheses, and that was my substitution for the normal force. We just put that in there just like we did in the previous part of the question, equals Max. And you'll notice the thing that's different now is we've got, for one thing, this acceleration in the x direction because it's going to be speeding up to the right at 5 meters per second. All right, now we got to get our FA by itself. This is the thing we're looking for. Everything else we know theta, we know mu k, we know theta, we know m, we know g, we know m, we know the acceleration. So it's, again, just a matter of now getting FA by itself. This is the, once you have it set it up with the physics concepts correct, this is just algebra now. We've got to be careful with our plus and minus signs. We're distributing this mu k inside again, but it's a minus mu k. So he's got a minus sign right there. You gotta be careful. So we got minus mu k fa sine theta minus mu k mg equals max. Careful. Okay. Now we can factor out our FA like we did before. We just have one extra term compared to the first part of the problem. But we don't have FA over here. We don't have FA in this guy, so we want to move this guy to the other side of the equation. All right, we're just practicing isolating variables right now. That's all that we're doing, isolating variables. Because it's sometimes tricky, but you work a few problems like this, and then you're like, oh, I'm pretty much just doing the same thing every time. Right? All the FA terms are now on one side of the equation, and the terms that do not have FA in them are on the other side of the equation, and this is done so that I can factor out FA. That is the point. Here's cosine theta minus mu k sine theta equals max plus mu k mg, and then we're getting FA by itself by dividing max plus mu k mg divided by, keep these parentheses here so that when I put in my calculator, I am not deceiving myself and messing up order of operations with the denominator. Be careful with that. Put it into your calculator a bunch of different ways. Solve the numerator by itself first, then the denominator, then divide them. Just, do it a few times. Make sure you don't do that this last input into the calculator part wrong. Let's double check. We know the mass, we know the acceleration, we know mu k, we know all these things on the right side. So we're good to go. Compare this to what we got over here when the acceleration was 0. Just to do a quick comparison, let's put them side by side. Over here, if you would. No, I don't want to type. No, I don't want to do that either. No, I don't want to. Okay, we're just going to leave that random O there for a second, I guess. Okay, can you? I don't even know. Goodbye. All right, so do this comparison here. In the bluish turquoise stuff, this is when the acceleration is 0, and this is when the acceleration is going to be not 0. In our case, we want it to be 5 meters per second squared. But notice the thing that's different is just this, which is added to the numerator there. So that means that my applied force is going to be not the same as what I got in the first part of the question. It's going to be the same plus a certain amount. So in orange, our second part of the question where the acceleration is going to be 5, we're going to get a bigger value for the applied force. That makes sense. We want it to accelerate, so we need to apply a bigger force. And how much bigger is it going to be? Well, that's being taken care of by the addition of this term in the numerator, the mass times the acceleration. And what we should have for that, let's move this guy out of the way because this bottom one was for the first part of the question. Over there. What we should get for this guy is 478 newtons. And we're going to check that together real quick. Show how we might put that in the calculator a couple ways. So one, I might just do the numerator first if I want to be very, very careful, because I don't usually use this type of calculator. So maybe I'm like, okay, you know what? Be very careful with this one. I got 50 kilograms as my mass times acceleration 5 meters per second squared. Then I want plus mu k, which is 0.3, times the mass again. Okay, so it's like, oh, I guess I could have factored that mass out in the numerator. Something I could have done. It's okay. Times 10, it's a little g. All right, so I got 400 in the numerator. Maybe I just make a little note up there. So now FA is going to be equal to 400 over, and then what's all this business in the denominator? I got to be careful. I'm going to open, even though I don't really need to right now. I'm going to open parentheses here. I got cosine. Am I in the correct mode? Let me check. Degree, okay, right? All these things are important. Cosine, not that application. 20 degrees. There's cosine 20. Close it up. Minus mu k is 0.3. 0.3. All right, then sine 20. Close. Let's take a look. So I've got 0.837, and we're going to think about that for a moment. Cosine 20 degrees, if I think about my unit circle, then there's going to be a fraction between 0 and 1, but it's going to be bigger than sine 20 degrees. Is going to be a smaller value. So I got a bigger value minus a smaller value. That smaller value is being multiplied by 0.3. So let me just think, if I do cosine 20, this is all just little logic checks. 0.93, if sine 20 degrees is really, really small, then I might have, like, the biggest thing I could have would be minus 0.3, which is not going to be, which would be 0.639. But sine 20 degrees, let's just check, this should be really small, right? Okay, so that times mu k, which is 0.3, is 0.1. Okay, this is making sense. So then if we go back and say, okay, cosine 20, that's the big value right here. This guy minus 0.1 means I should have around minus 0.8, 0.83, 0.837. What did I get? I got 0.837. Okay, so that's making sense up there. And then up top we had mass of, what was our mass of this thing? I keep forgetting. 50 times 5. Okay, so that's a pretty easy one. Plus a fraction of 50 times 5. So this is 50 times 10 because it's a little g. Okay. And then we've got 50 times 5. 40. Okay, so we're just putting it in multiple ways and double checking to make sure we're okay. Over 0.837. Because there are a lot of little calculator errors that can come up that are, you don't want to mess up because of the calculator buttons. All right, so there's our more specific answer. I rounded to 478 there. And then if we were to put it all in at once in our calculator, this is how I'd do it. 50, I keep forgetting the mass. 50 kilograms times 5 plus UK was 0.3 times 50 times little g. Okay, all that divided by. I got to make sure that everything downstairs stays downstairs. So I got to open it with a parentheses. Then I got cosine 20, close that up. But I still have my open parentheses at the beginning of the denominator, minus 0.3 sine, okay, what? 0.3 sine, let's go, 20, close, and then I gotta make sure I close it again to close off the denominator. And there I got 477.840. So 478, all the different ways I did it. Okay. All right. So there we did a few together there of the problems for our sliding friction. There are a couple more left here that are not going to be like what's on our test on Monday or Wednesday, whenever you're taking it. The main ones to focus on would be like the online problems we did, which are far more similar to these first couple of questions. You do want to be able to evaluate a problem where you have a force at an angle and you have friction, and then maybe a problem where you won't have friction. Make sure you pay attention to if something says constant speed, that means acceleration is 0. We showed kind of up here our 1, 2, 3 main things to pay attention to: free-body diagrams, and then solving for one of these values: acceleration, the applied force, kinetic friction, maybe mu k or the normal force, and mass, and those equations that'll be on our equation sheet. Okay, that's it for now. I hope that helps a bit, and I'll see you guys this week.